All right, so our final talk before a short break is going to be by HY. He's a PhD candidate in the AMP Lab, and he is the creator of Tachyon, and that's what he'll be talking about today.
Okay. So good morning, everyone. Thanks, Amit, for the introduction. So I'm Haoyuan. People also call me HY. I'm going to talk about this Tachyon system. It's a reliable, memory-centric distributed storage system. And on top of the slide, that's our logo, and the bottom, that's our website and meetup in the Bay Area. So here's the outline of the talk. At the beginning, I'm to give the overview of the project, including the first two core features we have, the memory-centric storage architecture and the lineage in storage. And then I'm going to talk about the open source status with a roadmap. So here's the overview. So Tachyon is a project from AMP Lab. We have many successful projects, say, for example, Mesos, Spark, this cluster resource manager, and paracomputing framework, which talked about by Mike, and Young at the beginning. And now we are doing this system called Tachyon. It's reliable, memory-centric distributed storage, enable memory speed data sharing. So then the question is, why do you want to do the system called Tachyon? So here's the reason. So memory is the king. On one side, RAM's throughput increases exponentially every year. On the other side, disk throughput increases slowly. This leads to the consequence that memory locality is the key to achieve interactive response time for big data queries. So this has been realized by many. So for example, from our lab, we have very successful project Spark, and there are other projects in the industry, and also blog DBMS2 also pointed out this is very critical to do this memory-centric computing nowadays. Then the question is whether the problem is solved or not. So luckily for a PhD student like me, the answer is no. So, so we are still missing a solution for the storage layer. Say if we can do a memory-centric storage, there will be a lot of applications, wide application on top of that. So here, let's use Spark as an example. As Michael said, Spark is a fast in-memory data processing framework. It keeps one in-memory copy inside the JVM and keeps tracking lineage used to derive the data. And when anything got failed, it just used lineage to recompute the data. Say, for example, if the map result got lost, simply recompute and get it back. So Spark is great. It has been widely deployed in industry and significantly improved the performance of many applications. But there are still several issues not covered. Say, for example, this is the first issue. In many companies, you have very complex data processing pipeline. And you will have the condition that you have one job's output will be consumed by the other jobs as input. So how do you do this nowadays? You use external storage system like HDFS, Amazon S3 to do this data sharing. So you can see that on the left side, this job generates some input and consumed by the right side. And from the animation, you can also tell it's really slow. So the problem is even more complicated. Say you have a new application written in Spark, but you have your legacy code you written maybe in Hadoop MapReduce. So you have to share how do you share the data efficiently among these jobs? That's the first issue. Then the second issue is, so nowadays in these frameworks, they share the execution in in-memory frameworks. They share the execution engine and the storage engine in the same process. This leads to the consequence that if the execution engine crashes somehow, you also crash your storage engine. You will lose your in-memory data. And you have to recompute it or load it from outside storage system, which could be time-consuming. That's the second issue. And the third issue is consider a very simple case. You have two Spark jobs. They want to read the same input data. And you want to cache the data in memory. How do you do this today? You have to load the data into every individual Spark applications. This means that you will have in-memory duplication. And because you run these applications on top of JVM, you will have a garbage collection issue, especially when you have a lot of data. So that's the third issue. So then, this Tachyon system, we enable reliable data sharing and memory speed within and across cluster frameworks and jobs to address above issues. Say, this is a basic solution for these issues. We have two core features for this to address these issues. The first one is memory-centric storage architecture. And the second one is we push the lineage down to the storage layer. So then we have the fact that we can only keep one data copy inside the memory, and we can also rely on the recomputation for fault tolerance if we want. So here's a stack to show where Tachyon sits in the ecosystem. It's a high-performance storage layer on top of existing persistent storage, such as HDFS, S3, GlossFS, and on top of that, you run all kinds of different computation frameworks, and we have close integration with frameworks like Spark. So then, this is the architecture of the system. We have a memory-centric storage architecture. We have one single logical Tachyon master, which keeps tracking the location of every single file, as well as monitor the status of every single node. And then, on every single Tachyon worker node, we run a Tachyon worker daemon, which manages the local space, as well as we run the RAM disk, which really store the real in-memory data. And then, when the Tachyon client has the data locality, it will access the RAM disk directly without going through another process to guarantee the memory performance. And then, besides one single logical master, we have standby masters and use Zookeeper to do master fault tolerant. This is our architecture. And then this is a lineage concept inside the Tachyon. It basically means the relationship among different files. Say, for example, you have file set A, and you have a Spark program with A and generate B. And later on, you have another Spark program with C and generate D. And in the end, you have a MapReduce program with B and D and generate E. And this whole relationship, including what's the binary program, what's the configuration, what's the input-output file list, this whole information is a lineage inside of Tachyon. And Tachyon has the ability to recompute the data if necessary. So this means that, when this application tries to write the data into Tachyon, it only needs to write the data into Tachyon's memory in one copy without any replication. And if something happened to the data, we need to recompute it. Tachyon has the ability to launch a job to do so. So because of these two features, Tachyon has this memory throughput I/O across different jobs and frameworks. And then let's revisit these issues. For the first issue, now we just different jobs or frameworks just do the I/O with Tachyon. Say in this case, as you can see, the animation is much faster than the previous slide. Yeah. So then the second issue is that now you also keep the data in Tachyon. So this means that if the execution engine crashes, it's also fine. You still have the in-memory data in Tachyon. Next time you load the in-memory data from Tachyon at the memory speed, and this is not a problem. This is very useful, especially when you do debugging for your applications. So for the third issue, we have a similar story. We keep the in-memory data as one copy inside of Tachyon, and then we have different applications. They just load the data, read the same in-memory copy, get the memory speed. And in the meantime, because we store the data off the heap in Tachyon, we will have much less overhead for garbage collection, have a much more predictable SLA. So that's the three issues. And then let's talk more about a little bit benchmark. Say we did a raw benchmark for write performance comparing with the in-memory deployment of HDFS. Say we did this experiment inside of an Amazon EC2 cluster with 30 nodes with 10 gigabits Ethernet. So the x-axis of the graph, that's the number of machines, and the y-axis of the graph, that's the throughput for writes in gigabytes per second. And as you can see that the blue line, that's the Tachyon write throughput, and the right line, that's the in-memory HDFS deployment. And you can see the performance gap here is around 100x. And then we did a theoretical analysis. What's the best performance you can get if you do replication-based write? And you have to go across the network, which will become the bottleneck. That's the green line. And this, you can see the gap is still pretty significant. After running this raw benchmark, we did a realistic workflow on top of these different deployments. This workflow is from internet company. It's a log analytics framework, contains 400 Spark jobs. And we run this experiment on 3 different modes. The first bar, we run this on top of in-memory deployment for HDFS. And then the last 2, that's the Tachyon deployment. The difference is the middle line is we failed a node during the execution and see how long it takes to finish all the execution and get all the data back. And the last bar, that's run on top of Tachyon without any node failure in the cluster. As you can see that no matter with failure or without failure, if you run this on top of Tachyon for this workload, it's around 4x performance improvement. But here I want to point out is, so the real workload improvement depends on the workload. Say for example, if you have a much more CPU-intensive workload, you will see a much less improvement. On the other hand, if you have even more I/O-intensive workload, you will see higher performance improvement. Okay, so besides showing the raw benchmark and having some demonstration of how the workflow performs on top of Tachyon, now we want to show that Tachyon can also help a single in-memory program shop's performance. And here we use Spark's grep application as an example. We run this grep application on a single EC2 node with 240 gigabytes memory. And the bottom graph of this slide is the enlarged left area of the upper graph. And the x-axis is the raw data size in gigabytes. And the y-axis is the execution time for the whole program. And we run this in 3 different modes. The first one is we run Spark Cache and store data in the deserialized format. And then the green line is the Spark Cache in the serialized format. And last one, TFS, we run it on top of Tachyon. As you can see that at the very beginning, we have a small data, comparatively small data. Spark Cache mode has the best performance, especially for the deserialized mode, because it doesn't have the serialization, deserialization overhead compared with other 2. But slowly, when you increase the data size, you can see that for the deserialized mode, it cannot execute on more than 40 gigabytes raw data. And that's because when you put the data in the Spark JVM as the Java object, as a much higher memory footprint, which will trigger a lot of garbage collection issue, which will screw the performance. You have a lot of data. But later on, you will see that around from 70 gigabytes data, by using Tachyon, you will have Tachyon leads the performance if you use Tachyon and provides you very predictable SLA. Okay. So then we talk about the architecture of the system. We talk about the first 2 core features, and we talk about some initial benchmarks results. And the question is how hard or how easy to use this system. And we want to show that in the following slide. This is how you use different frameworks like Spark, MapReduce without Tachyon. Say, for example, the first line, you got a Spark RDD by call a text file from HDFS URI. And now with Tachyon, you simply change the URI from whatever previous URI to the Tachyon URI, and it will just work. So it's basically configuration change, and it's relatively simple to do this. And also, besides doing this input-output with Tachyon, a framework integrate more with Tachyon will get more benefits and leverage features provided by Tachyon. So in this case, we use Spark as an example. As you can see that besides having input with Tachyon, write output out into Tachyon, and you can also store the RDD as the off-the-heap storage into Tachyon. That's the feature from Spark 1.0. And this will give you more predictable SLA and also improve performance when we have more data. Okay, now let's talk about the open source status of the project. So we started the project from Unplug at UC Berkeley from the summer of 2012, and this is our initial research team. It's me and my colleagues Ali Gozi, Matej Ziharia, and my co-advisors Jan Stoika and Scott Shanker. And we have our tech report and the papers you can search online if you want to know technical details. And after that, we open source this under Apache 2.0 license. And the latest release is July this year, version 0.5. And just to prove this is real, we have a snapshot of our GitHub. And now, from the statistics several months ago, the project was deployed more than 50 companies, and there are more than 20 companies contributing to the code base. Normally, I would ask how many contributors in the project now, but Yang talked about it in the earlier talk. So also, another thing is if you have Spark or MapReduce applications, you can run on top of Tachyon without any code change. You can just plug in, you get a lot of benefit. That's a great thing about the system. So then, Yang also talked about the slide, so I'm going through this very quickly. So this is our release growth. We had 1 contributor at the beginning, and we have 300% improvement. And then, yeah. And then we had, thank you. So then we had 15 contributors for 0.3, 30 for 0.4, and the latest 46 for 0.5. And now the number of contributors is close to 70. And as Yang mentioned, we are very proud of that. We have very open and friendly community. And more than 80% of the contributors now came from outside of Berkeley. And I got emails every day asking about how to contribute to the project. And we are very welcome to all the possible collaborations. And I want to take this opportunity to thank all our code contributors. And this is a list, maybe a little bit out of date. And this is a partial list of the company which are contributing to the project. And the great thing is that several of these companies, they have committed full-time resources into the project, work on this on a daily basis. And a lot of them are considering increase the resource next year. And another great thing is, thanks to Red Hat, now Tachyon is also in Fedora channel from Fedora 20. This means that if you have a machine connecting to Fedora channel, you can install Tachyon by using 1 command. And also, the company called Tachyon, they have Tachyon in their commercial big data platform, and they deploy this in dozens of their customers' clusters. And they showed me their 1 snapshot, and 1 cluster has deployed Tachyon for more than 9 months without any problem. And also, as I mentioned earlier, now Tachyon is the default off the heap storage solution for Spark. If you use Spark, it's very simple to leverage the feature of this project. And we are working more to integrate more closely between the projects. And also, as I mentioned in the previous stack graph, you can share the data between different frameworks using Tachyon. This is 1 example. And this company, Data, they have their own framework, and they call H2O, and they use Tachyon to share the data between Spark and their framework H2O, which is great. And also, as Yang mentioned, we got more and more supports from industry. 1 month ago, Pivotal and the EMC announced that they are going to have Tachyon in their future architecture of the data lake, and which also play an important role. And say, for example, many news report this, like GigaOM saying Pivotal and the EMC are betting on Spark's cousin Tachyon as in-memory file system. And also, so Tachyon has this under file system concept. This enables the system to reach wider communities. Say, for example, the Gloucester community announced early this year saying they integrated Gloucester file system with Tachyon. This means that if you have Gloucester file system deployment, you can run Tachyon on top of that very easily without moving your data. And then you will be able to reach a you'll be enable much wider applications on top of that, run all sorts of big data workloads and many more we're building. And besides, as I mentioned, Gloucester FS, we also support HDFS and Amazon S3, and people have production deployment on top of this, either HDFS or R3. And in the meantime, we have other prototype already working, which will be in the release pretty soon, like Ceph integration, like NFS integration, like OriginFS integration. So this means that people can run Tachyon beyond big data. You can run Tachyon in the cloud deployments, and you can run Tachyon in HPC, and you can also run Tachyon even for enterprise. And actually, there are already like cloud company and HPC company and of course enterprise company are working on like integrating this into the ecosystem and leverage the benefit provided by the system. Okay, and now after talking about the open source status, let's talk about a little bit about roadmap. So this is the big feature we already have. We have memory-centric storage architecture. We have the lineage in storage. And now we're adding this feature, hierarchical storage. This is a very critical feature for the cloud deployment. This feature will be in 0.6 release. This means that besides managing memory, you can also manage SSD disk on top in the same machine as the local storage. But in the meantime, we still require a persistent storage as a backend of Tachyon. And also, beyond that, after storing data into Tachyon, we want to think of how can you serve the data better to the upper layer. This is another thing we are actively looking at, which is the data serving. And also, we're also looking into different hardware, like how to better support different hardware. Say, for example, like InfiniBand, like RDMA, like even NVRAM. And say, for example, Mellanox, they already had a patch for Tachyon to work with InfiniBand and RDMA. And of course, there are many more features. And if you have any requirements, you should feel free to come to us, either post it in our forum or just email us about your requirements. That's our big features. And to show a short-term roadmap, this is for our 0.6 release, which will come out in either December or early January. And this is a partial list of features we are going to have. Most of these features, they are a multi-organizations like effort. But I only put the lead party behind the feature. So for example, the Ceph community, they are working on the Ceph integration, and Intel is leading this hierarchical local storage, and Yahoo is working on the performance improvement, and Red Hat, they are doing this easy deployment to deploy in many different environments, even our local machine as a cluster. And then in the MPlab, we are working on many stuff. One example is multi-tenancy. And Databricks is working on further improvement integration with Spark. Mesosphere is doing the Mesos integration, and Pivotal, they are doing the improvement for the network subsystem. And there are many more from us and our industry contributors. Okay, so I got this question quite a lot. So people ask, what's the goal of this project? What's the long-term goal? So the goal of the project is that we want to better assist other components in the whole stack. This means that on one side, we want to support more frameworks. Say, for example, now we have Spark, MapReduce, H2O, and we are going to support better for others too. And this means that besides bringing the performance benefit, we are going to also investigate to provide better ways for the upper layer to access the data in the storage layer. And on the other side, we are going to integrate with different persistent storage systems. Like now, we already have HDFS S3 and the GlassDFS. There are many others like coming in the next year. And the story for this side is similar. Say we are going to boost the performance of this integration, boost the performance of the storage layer. In the meantime, we are going to enable this different persistent storage system to reach a much wider workload. And as a user, if you already have a persistent storage like deployment, you don't need to move your data anymore. You just deploy Tachyon on top of that, you'll be able to run a lot of different workloads like immediately. You don't need to move your data anymore. And so keep in mind the potential of the system to work beyond big data. Like we work in cloud, in HPC, and also in enterprise. So with that, I would like to welcome Annie and our collaborations. And if you want to know more about the project, please visit our website, our GitHub, and our meetup group. And also feel free to email us. Thank you. Sure. Oh, whether Tachyon can run on different hardware, like in the same cluster. Yeah, we didn't really explore this like extensively, but it's doable. Like it's just a configuration now. But we didn't treat this differently.
So if I'm using abstract Spark,
Mm-hmm.
if I'm not using Tachyon, I really don't worry about the size. It's going to chunk the data out and write what's going to happen across the clusters. So it's just a matter of time. Clearly, there are limits to memory the size of RAM is. Am I going to have to be clever now and manage how things get chunked out?
Are you asking how to allocate the memory between Tachyon and Spark?
Well, I wonder how stupid you're going to be as a Spark programmer.
How what?
How stupid.
Oh,
Can you repeat the question, though?
How easy?
how easy for Spark application to use Tachyon?
So, the RAM is only so big, right? Still.
I see. So, but basically the question is still like you have limited memory, how you allocate the space between different like Spark between Tachyon. Yeah, so we don't have we haven't done any like extensive study here, but from what I've seen is that people just, so when you use Spark, you can compute like how much like how much memory Spark needs for the applications, right? So after computing that, you can leave the rest of the space to Tachyon. And also, it also depends on what's the size of the machine. So for example, in the long run, per CPU memory size is growing. And also a lot of current deployment, they have 192 gigabytes per machine, or even like 200 gigabytes per machine. And some company, they have 4 terabytes. And in the long run, you see in 3 years, all these machines, they will have at least 1 terabyte. In that case, it's much easier to do this job. You just allocate maybe 800 gigabytes or 900 gigabytes then. But now it's kind of harder. But you need to do the developer or the DevOps people, they need to do the computation. How much memory does the Spark need for this case? And you leave the rest to the storage layer.
All right, so we have a 15-minute break now. Feel free to ask HY questions maybe during that break. Also, Michael's around through the break, but then has to head out. So if you have Spark SQL-specific questions, bombard him in the next 15 minutes. Okay, so we'll see you guys all in 15 minutes. Thanks.